Hey there, chemists. Today we're going to look at some applications of the aldol reaction and focus specifically on aldol addition reactions. Remember, that's the reaction of a ketone and an aldehyde to give you a beta hydroxyketone. And I want to show a generic example first. Remember, you can imagine forming an enolate alpha to a ketone that would attack an aldehyde. Electrons would go up. This is a lengthy mechanism, but I'll just show the product. You form a new carbon-carbon bond, and I would have a ketone, in this case a methyl right there, and a new alcohol right there. Now this particular example, because I'm stopping at the addition product, we have two asymmetric carbons. And if we just draw all possibilities, I could have the methyl coming toward me and the OH coming toward me, or I could have the enantiomer of that with the methyl going away and the OH also going away. Or I could have diastereomers of this compound as well. So let's draw them just for completeness. I could have the methyl coming out of the screen and the OH going into the screen, or the enantiomer of that, which would be the methyl going into the screen and the OH coming out of the screen. So I have at least these four possible stereoisomers just when I consider the addition product from this reaction. And if you think about it, I was sort of arbitrary in enolizing to the right of that ketone. What's to stop me from enolizing on the left, which means I would have a whole other set of constitutional isomers as well. That would only give me two different stereoisomers, but that means there's at least 6 products just for the aldol addition reaction. And I can't enolize that aldehyde, but you can imagine an enolizable aldehyde, and then you have an even more complicated scenario. So what I want to go through today are a couple of ways that chemists have come up with to control the outcome of a reaction such as this one. I'm going to start with what I'm calling regioselective control. How do we know if we enolize on the left of a ketone like this versus on the right? This is not a symmetric ketone, and I could potentially form both enolates. Well, we can control that just with temperature. So remember, LDA is that large base that's not a nucleophile, but it will deprotonate a hydrogen, and you'll form an enolate. And if you let this simply warm up to room temperature, you get what turns out to be the more stable enolate, and that's the one I just drew. The alternative is the one below it. -78 sounds a little bit of a arbitrary number, but that happens to be a mixture, an equilibrium mixture of acetone and dry ice solid carbon dioxide. So you can very easily make a very cold temperature bath in an organic chemistry lab. If you cool this down and you only give it enough energy to form not the most stable thermodynamic enolate, you'll form the less stable enolate, but the one that's easier to form in terms of abundance of H's. There's more H's on that methyl than there are on that methylene, so we actually get an enolate on the other side. Now, it might be difficult to see why one of those is more stable than the other, so to answer this, we need to look at the more significant resonance contributor of each of these. Remember, the enolate might behave by attacking from that carbon, but its preferential resonance contributor looks like this, with the oxygen bearing a negative charge. And if I do that for both of these, then we uncover why one of them is more stable than the other. And there's a giveaway in the title of this section, non-Zaitsev versus Zaitsev. This is the Zaitsev enolate, because I have a more substituted carbon-carbon double bond, and right below it is the non-Zaitsev. So we call the first one the thermodynamic enolate. Because it is more stable. The one below it we call the kinetic enolate, because it forms faster. And that's just because of the probability of finding one of those 3 hydrogens as opposed to the other 2. That's a little bit of an oversimplified explanation as to what's going on, but the point is just changing temperature lets you control what kind of enolate you can get from an unsymmetrical ketone. So that actually narrows down whether we get these 4 or those other 2 products that I just only mentioned from enolizing on the other side of that ketone. What about some of the stereoisomers? Can we narrow down some of the stereoisomers? Yes, we can. This has to do with the olefin geometry that's buried inside the more stable enolate. For this, I'm going to use a different ketone. I'm going to actually use a symmetric ketone, so we don't have that Zaitsev versus non. And I've actually already got a lot drawn on here. This we change with reagents. So here we have an enolizable ketone, and we're making a special type of enolate called a boron enolate, which is overall neutral. We have an example of each, actually, if you look. And that's just, instead of an O negative, it's actually forming a bond with a boron that came from this reagent. Those are just butyl groups. That's what Bu stands for. OTF stands for triflate. It's similar to a tosylate, so it's kind of like a leaving group. So this is a boron that's quite electrophilic. So it can get attacked by the resultant negative charge that ends up on the oxygen. The triflate group leaves, and you get a new oxygen-boron bond. And what we have are effectively an E version of the enolate down below, and a Z enolate. These are almost the same enolate, almost same type of intermediate, except the alkene geometry is reversed. We have Z, same side on the top, and E opposite sides on the bottom. And the thing that changed it was simply what type of boron reagent that was used. A very linear boron compound with these not very sterically and cumbersome butyl groups allows for the formation of this Z enolate. But if I switch to a dicyclohexyl, that's what CY2 stands for, and replace those butyls with cyclohexyls, those are very large, so that shoves this methyl out of the way, and you preferentially get what turns into the E enolate. And this translates into the relative stereochemistry of the product, and we're going to explain why. I just want to absorb what we get here. The Z enolate gives us the syn product. The E enolate gives us the anti product. So you can imagine going back up to the example way at the top, we had 4 stereoisomers drawn. 2 of them could be classified as syn, 2 of them could be classified as anti if we drew them analogous to what we have in front of us here. You would get the racemic mixture for each of these though. So of those 4 original products, we've narrowed it down to 2, and cut it in half. Why? Why does the Z enolate give us the syn, and why does the E enolate give us the anti? For this, we have to look at a chair transition state, much like the reactions we looked at before. So I'm going to redraw that enolate. Here's the oxygen connected to a boron. And that enolate has, if I look at what it looks like on the left, there's like an ethyl along for the ride, and I have a methyl right here. And then it will start to form a bond with the aldehyde, which I'm going to draw in the hydrogen and the phenyl. And I'll fill in that H as well. There's a new bond that's about to form between the oxygen and the boron, and we have our butyl groups. This is a, I hope you can tell, chair transition state for that reaction. There's the enolate right there, and there's the aldehyde. And it's no coincidence that I am positioning this phenyl in a pseudo equatorial position with respect to that chair. So let's draw the product that we get from this after the reaction occurs. Those dotted lines sort of already show me what I get. Draw everything the same and just change what's changed. Ethyl along for the ride, that methyl down there. It's actually a new boron-oxygen bond, isn't there? With these butyl groups still there. And then what else? My phenyl is right where it was. And then where are the hydrogens? There's one there, and there's one up there. So look at the position of those hydrogens right there and right there, or anything else, and try to redraw this molecule. You'll actually see you get exactly what we have right here. The oxygen-boron bond gets hydrolyzed to an OH. Gets hydrolyzed. That would be in a later step. to OH group. So the overall reaction is not just one step, but those stereocenters are formed in one step. So that's why this chair transition state is so important. So I want you to challenge yourself and see if you can draw the analogous chair transition state for the one right below it. The only thing that's different is that the enolate that you have is E. That's the main difference. I mean, the butyl groups are cyclohexyls, but that's the main change. So hit pause, try to draw that, see if you can explain that we get the antiproduct instead. Okay, let's see how you did. So I'm actually going to mimic what I have right up above. Start with the enolate. There's like an ethyl up here. There's an oxygen connected to a boron. And then there's a new carbon-carbon bond about to form with the aldehyde. The aldehyde, you'll notice, is actually what makes up the rest of the chair. I've got a pseudoaxial H on the aldehyde, a pseudoequatorial phenyl on the aldehyde. This time on the enolate, that H is pointing down, and the methyl that's on the end of that enolate alkene is what looks to be pseudoequatorial. These are cyclohexyls. I do the aldol, I do the actual reaction, and that becomes a single bond, that becomes the ketone. That ethyl is still up there. There's my new carbon-carbon bond. There's my new carbon-oxygen bond. The oxygen boron up there is no longer formed, but there's a new oxygen boron bond there. I have on what used to be the enolate an H straight down, a methyl pseudoequatorial, and then on what used to be the aldehyde an H up pseudoaxial, and it's all about the approach of that aldehyde and getting that phenyl, the R group on the aldehyde, so that when the aldehyde approaches the enolate, which they do face to face, that phenyl adopts a pseudoequatorial position. That's the whole point of having the syn product from the Z enolate and the anti-product from the E enolate. If we reversed how that aldehyde approached and I put that phenyl up here in a pseudoaxial position, you would get the other diastereomer. But that's not what we observe. We observe syn from Z and anti from E. So easy to remember actually in this case. The Z gets you the zin aldehyde, or zin aldol product. So if you're really following that, there's actually one other question you should ask yourself. When you drew this transition state, let's just look at the first one. I have the aldehyde approaching the enolate from the front of the screen, let's say. What's to stop it from coming from the other face? And the answer is nothing. That's actually how you get both enantiomers out of this. That's why I wrote the plus minus symbol. So we have that approach, equally likely, they'll both be the syn product, but I get both. Is there a way we could get just one of those enantiomers? Can we get enantioselective control? And the answer is yes, we can. There's a number of ways to do it, but one of the most well-known ones is called the Evans aldol. And the way you get this is you put chirality in the molecule ahead of time. You actually start with a chiral, not just chiral, but an enantiomerically enriched source of an enolate. And let me show how this works. So this is called an oxazolidinone. It's derived from naturally occurring amino acids, and there is an enantiomerically enriched stereocenter. Let's write down some of that. Made from natural, occurring amino acid. I want to say phenylalanine derived, likely, I'm not sure, but probably something like that. And what happens is when you treat this group, which we're going to call a chiral auxiliary, because we're going to put it on and take it off later, the base deprotonates this oxazolidinone. You'll get an anion on that nitrogen. I'm going to abbreviate this. That will then do a substitution on this acid chloride, and that makes this a big difference. We're actually starting with an acid chloride instead of just like a ketone or something. So, and you'll see what we get out of this. This turns into what looks like an amide at first. And we've substituted For the chlorine, this entire group, so right there is what I meant to say, looks kind of like an amide. And the arrow pushing for that, very similar to the chemistry that we saw for amide formation. This is not called an amide, it's more complicated than that, but you can think of it that way. And I'm actually going to abbreviate this because what's on the left-hand side here isn't going to chemically do anything for us. It's going to physically do something for the arrangement, the orientation of the molecules. It's a big steric group, and I'm going to abbreviate it as X sub C for chiral auxiliary. Chiral auxiliary. So let's see an example of this and what happens. There's actually some fancy looking transition states down there that I'll draw attention to in a moment, but let's just show what happens. If you use what used to be an acid chloride, this chiral auxiliary containing carbonyl, and we make a boron enolate, as we saw right above. I'm going to use the dibutyl boron chloride in the presence of some base. That's just to soak up the HCl that's formed. That'll get you to a boron enolate. And remember up above, we said that if you have the butyl compound, you can get the Z enolate. The only difference is now this one is chiral. It's got this auxiliary in it with its own aspect of chirality. And then if I treat this with an aldehyde, and I'm going to use a very generic aldehyde, just with an R group, followed by a hydrolysis of the borate that forms, you get an aldol product, which is a new carbon-carbon bond. Now the Z enolate gives us a syn relationship between those two stereocenters. That's what we just talked about above in the previous part. The difference here is because of this auxiliary, you only get one stereoisomer. Only one stereoisomer formed. So, and the reason for that is shown a little bit over here. Now what this does is this controls approach of the aldehyde to that boron enolate from one face, and it's because of that existing stereocenter. So here is the same or a very similar chair transition states to the ones we actually drew up above, and you can see that there's an approach on one face of the enolate versus the other face, just sort of turned it around. In both cases, we have the R group of the aldehyde in a pseudo-equatorial position. That's what it's going to give us the syn relationship in this case, there and there. But we have a favored case in this example, and it's just because of that asymmetric carbon. You can even see a little bit why, perhaps. That benzyl group, BN, by the way, stands for benzyl, which is a phenyl CH2 group attached to something. It's phenyl plus a methylene. So it's just a large branch attached to it at that position. It's blocking the back of this particular enolate, so that aldehyde comes from what I'll call the front in this case. That's why we get such selective bond formation. So to recap, the syn relationship, and we'll use this example as a way of recapping. Recap. Syn relationship came from the Z enolate. The absolute configuration, really of the OH stereocenter, that's what we did there, controlled by chiral auxiliary, XC. And then if you want the other stereoisomer, use the other enantiomer of that auxiliary. You go back to the beginning, this was the S-oxazolidinone. What if I want the other stereochemistry at that OH group? I'll switch this to R, and that's the whole point. In fact, let's circle that with a different color. The S-oxazolinone is what turns into that stereochemistry right there. Want to change this? You switch the stereochemistry of that oxazolinone. Let's actually add one more thing to this, because you should be looking at this and going, great, what do I do with this chiral auxiliary now? Unless I want to make a molecule that specifically has that in it, how do I get rid of that particular group? Well, there is a way to do it. So to get rid of the auxiliary, I actually will put that up here just as a little side note. So if we have your aldol product with the auxiliary intact, and I'll show it with the one we actually made, the syn relationship. There's many things you can do. I'll show you two things you can do. One, you can treat this with a peroxy base, lithium peroxide. That'll actually convert the auxiliary into a carboxylic acid. Everything else stays the same. So we can imagine functionalizing that carboxylic acid in a variety of ways. Or if you want to make it look like a more traditional aldol product, in other words, get it back to a ketone, this takes two steps. Number one, you have to turn it into a special type of amide using methoxymethylamine. That looks like methyl, I'm going to write it down here, methyl NHOME. And then step two, that turns it into what's called a Weinreb amide. And amides prevent over-alkylation. Then you can treat this with a variety of organometallics, for example, a cuprate or even a Grignard. And what that does is it replaces the auxiliary with whatever your new R group is, methyl cuprate, phenyl Grignard, things like that. I'll call that R prime, and you get a ketone. There was another R group along the ride the whole time. And that's perhaps a very useful thing. That's probably the most useful thing that we'll use, because now I have what looks like a typical aldol product from when we first learned this reaction. Okay, so we can control which type of enolate we form, the E or the Z enolate, based on the boron reagent. We can even control what an enantiomer we get in the end. So from a starting point of a lot of different possible products, we've been able to narrow it down and control to just get the one that we want, which means when we do this in the lab, we are in control of what comes out of the reaction. That's what chemists want to do when they make reactions. That's the aldol reaction.